for being here. As I see lots of the participants starting to roll in. Welcome to the spring semester and another hopefully slightly more successful attempt at having a full complete semester here at NC State and everywhere else in the world. I'm going to first things first is I do want to just give you a quick update. Next week, our speaker is going to be Harsh Desai, who's an alumni of our department, who currently works over at NEI, and we'll be talking about nuclear power for hydrogen production. This week, we have one of our own presenting, Dr. Jason Ho from NC State University, from our own department, who I'm sure you all know, who is an assistant professor of nuclear engineering here in our department. Prior to joining us, he was a postdoctoral scholar at UC Berkeley in their Department of Nuclear Engineering. He earned his PhD and master's degrees in nuclear engineering from Penn State and the University of Michigan, respectively, and received his Bachelor of Science degree in engineering physics from Tsinghua University in China. So his area of research includes multi-physics reactor simulation, advanced reactors, fuel cycle analysis, uncertainty quantification, machine learning, and engineering applications, nuclear power plant simulation, and just about everything else nuclear you can do on a computer. Presently, he's performing studies on the high-to-low informing scheme for multi-physics simulation, doing sensitivity and uncertainty analysis and modeling for various reactor systems, looking at high-fidelity reactor core simulation, hybrid Monte Carlo and deterministic methods for polar calculations, machine learning for plant prognosis and diagnosis, and is the coordinator of the NEA OECD homogenization-free time-dependent neutron transport benchmark. Within our department, aside from being a professor in our department, Dr. Ho is also the director of the Research Dynamics and Fuel Modeling Group and serves as a coordinator for our nuclear simulation laboratory. So with that, good to see Jason, as it's always good to see Jason, and I hand the floor over to him for what's going to be an awesome presentation. Thanks for everyone's attention.
Thank you, Steve, for the introduction. I should have given you a shorter bio, but I hope, just a quick summary. I'm a reactor guy. My research is centered around the nuclear reactor. I do modeling and simulation. And of course, related to that topic, there's also model, verification and validation, uncertainty quantification, sensitivity analysis. I also work on the reactor design and analysis, optimization. So a reactor guy. I'm the director of the Reactor Dynamics and Fuel Modeling Group. We have 3 faculty members, a few research scientists and postdocs, and over 20 graduate students. So it's a fairly large group. Today, the work I'm going to present here actually consists of 2 parts, coming from 2 ongoing projects, or the project we just did, which involves several people from the group. You'll see the name and their contribution. So the title is Consistent Uncertainty Propagation in Reactor Modeling and Simulation. Let's get started. So the idea of the uncertainty quantification, or why we need it, is really easy to grasp. I'm giving you such a very simple example here in this plot. I'm trying to find the pointer. Okay. All right, over here. Let me just shut down camera for a better audio quality. Okay. So here's a very simple example. Suppose you're running your reactor and you know there's a safety limit, for example, the fuel temperature. You don't, at the very least, you don't want melt your fuel, right? So you absolutely cannot go beyond this point, and regulation will tell you, okay, you must maintain some safety margin. So you must have a certain distance from the maximum of your reactor to the safety limit. Okay, this red solid line is somewhere you never want to cross. Now, your real value during the operation could be here. That means you have a lot of room, between the real parameter and then the value of the parameter and the requirement. Now, do we want to increase or decrease this margin? We certainly want to decrease this because larger margin means higher penalty and there's a price to pay. When I say price, I literally mean there's a lot of money in that gap or in that margin. But when you do the safety analysis, usually or previously, people rely on this conservative model or calculation. They say, okay, we don't use the best knowledge of the data or model. Instead, we impose some very conservative rules or standards so that you may end up, through your calculation, a value over here. That means you have a much reduced margin. But it is not realistic. A more realistic way to do this is to use so-called best estimate model and data. That means relying on based on our best knowledge of the physics and the validated model and the data to perform the calculation, and you may end up a value over here. Okay, that is somewhere between the real value and the conservative calculation results. But as you use the best estimate model and data, there's always a question of whether or not your uncertainties, whether it's the input data or is related to the boundary conditions, such as operating conditions, are they considered in the calculation? So that's why we, on top of the best estimate model and data, we will impose those uncertainties. We want to propagate the uncertainties through the calculation or simulation scheme and to the quantity of interest, usually the system responses. And so that's where this error bar is coming from. And then, since once you have this best estimate plus uncertainty results, you can get a realistic licensing margin, which is shown here. Okay, this slide shows very general uncertainty quantification framework. You see, this is pretty much from the input to output. The input uncertainties are usually given in the form of sort of PDF, sort of distribution. And you may have, in realistic case, you may have multiple input parameters. They may be independent and may be dependent or correlated. And then you propagate this uncertainties through your model, through your calculation scheme. And the end, you get your output. You analyze your output statistically, you get the distribution, for example, of a system response. And from there, you get the mean, you get the standard deviation, or you get something else to describe the results or the uncertainties in a way that is accurately represent the nature of the problem. So in the middle, you have this models, the numerical models that you use to simulate the system. You have a code. That code can be a single physics code or a multi-physics coupled code system. You prepare input based on input uncertainties and you get output. And from there, you get your quantification of the uncertainty for the output quantities. And then you can also perform a sensitivity analysis. This is the opposite direction of the data flow I just showed to you. Here, you can really find out the importance of input parameters and their influence on the output quantities. So basically, how the change in input parameters affects the output results. Now, the models are really reactor dependent. For example, the light water reactors and fast reactors, just because of their distinctive nature of physics, um, different type of modeling approach have been adopted. And so that means your uncertainty quantification method should also comply with the modeling and simulation approach, which is customized to different reactor systems. So this is something that I want to emphasize. If you look at the input uncertainties, as I mentioned before, these can be independent, but in many cases, they are interdependent, which means changing in one parameters would affect the value of the other. So how do you propagate the uncertainty consistently? Meaning, how do you consider the correlations between input parameters in either a single physics calculation or multi-physics calculation? It's something that we want to address. Now, if you look at the modeling and simulation approaches for light water reactors and fast reactors, they're largely determined by the physics, by the nature of the problems you are presented with. Right? For the light water reactors, in most cases, we follow a two-step. This is neutronics calculation, the two-step lattice and core calculation scheme for neutronics, where you get your lattice calculation and done, and to generate the multi-group cross sections for the core calculation. Note that the cross sections here are usually so-called parameterized cross sections where thermohydraulics feedback are embedded in those multi-group cross sections. So your cross sections are prepared at different conditions. For example, fuel temperature, moderate density, control rod position, etc. And then you perform spatial kinetics core calculation. Then you couple neutronics, thermohydraulics, and fuel modeling or fuel performance calculation. On the other hand, you have fast reactor technology, which is quite different from light water reactors. Most notably is that in the fast reactor, neutron mean free path is much longer. Neutron can travel longer in the fast reactors. So you don't really have large variation of the flux spatially, as much as in light water reactors. So you can really simplify the calculation scheme by just calculating the so-called reactivity feedback coefficients. So how much, for example, I give you an example as Doppler feedback coefficient, which is the change in the fuel temperature and its impact on the reactivity, right? So once you get this reactivity feedback coefficients, you can run a simple model based on point kinetics and to perform transient calculations for the system. So both of them are, you can also extend this to a multi-physics framework for the fast reactors. But at this moment, we have more experience in code development for the light water reactors than for the fast reactors. So incentives. In most of the best estimate plus uncertainty approaches, we consider the various uncertain input parameters to be independent from each other. So, which means the correlations between those parameters are not considered. So that means their impact on the uncertainty of the system responses are also believed to be independent. Of course, we know it is not true, and this will introduce biases as uncertainties originating from the same fundamental sources are in fact make them correlated. And so we really want to find a way to propagate the uncertainty consistently through the calculation scheme. Usually it is multi-step. So in this presentation, I'm trying to give you two examples from the two projects we just did recently and give you an idea. How do you do this for the light water reactor and how to do this for fast reactor, according to their corresponding modeling and simulation approach. Note that there will be a lot of details missing in this presentation just because of the constraint of time. I would encourage you to check out the references I mentioned in the presentation for more details. So the first one is a case study on a light water reactor application. Dr. Kaiyue Zheng, who just graduated from NC State last summer, is the lead of this project, and Dr. Gregory DeLepe, who is a postdoc scholar in the group, helped a lot in this project. And myself and Dr. Allen also participated in the study. The PhD dissertation from Kaiyue is available online. You can check for more information. So this work is actually, excuse me, is actually done within the framework of so-called light water reactor UAM benchmark. UAM stands for Uncertainty Analysis in Modeling. Now, this is the OECD NEA benchmark, has been running for 12, 13 years already. This image here shows the general framework of the multi-physics uncertainty quantification or propagation method we have developed in that framework of the benchmark. So basically, you have neutronics, fuel performance, and thermohydraulics calculation as the initial step, and then in a coupled calculation, you try to put the uncertainties together in a consistent way, and you're trying to analyze the system performance in terms of their uncertainty. Now, as I mentioned before, the problem is that if you consider the multi-physics correlation, you do not consider the multi-physics correlations, you may introduce biases in the calculation. So we're trying to address this by coming up a method for the uncertainty propagation. So in what cases you may see these correlations? This picture shows the sources of different physics in the light water reactor simulation. I break it down to three area. One is the neutronics. The middle one is the fuel modeling or fuel performance. The last one is the thermohydraulics. Let's take one example. The fuel pellet diameter. Okay, the fuel pellet diameter would certainly have impact on the cross sections generated from the lattice calculation, because that effectively change the amount of fissile materials in the homogenized model. And it would also change the fuel performance of fuel modeling calculations because it has an impact on the heat transfer. Then it would also have influence on the thermohydraulics calculation because, well, some of the thermohydraulics input parameters may change because of the variation in this parameter. So you see, if you look at just the input uncertainties for the second step of the core calculation, multi-physics core calculation, you don't really see the impact of the fuel pellet diameter or the size really would have changed cross sections, heat transfer related parameters, and thermohydraulics related parameters. So for those parameters which are input to the core calculation, they're certainly not independent. So some correlations has to be taken into consideration. So right now, or before we started this project, the usual uncertainty quantification in the approach in the multi-physics calculation looks like this. So you do you perturb the nuclear data based on their variance covariance matrix. You perform lattice calculation. You get the multi-group constants or the cross sections. And at the same time, you perturb the field modeling and the thermohydraulics calculation, or field modeling and the thermohydraulics parameters based on their distribution independently. And then you get a number of perturbed parameters. You combine them, both sides, in the multiphysics core simulation, and after that, you perform statistical analysis. You get the mean and the standard deviation, for example, of the system response. But in order to take into consideration of the the correlation of those input parameters, we really need to construct, or at least one way to do this is to construct a global variance covariance matrix that which takes not only the variances of those, but also the covariances of those parameters, and then we can resample this variance covariance matrix before conducting the multi-physics core simulation. This is another way to look at this, is really when we sample the initial parameters, or the first set of parameters required by the calculation scheme, we sample all of them together at the same time. So this includes the modeling parameter, geometry parameter, and nuclear data. And then by doing so, we kind of consistently perturb those variables before feeding them into neutronics, field modeling, and the thermohydraulics calculation. And then after that, we construct this global variance covariance matrix. Afterwards, we resample them and feed those into the core multiphysics calculation, and then we analyze the output responses. A typical global variance covariance matrix may look like this. You have neutronics part on the upper left corner. You have the thermohydraulics and field modeling on the lower right corner, and you have the covariances between those two as marked as 3 and 4 in the matrix. So this is another way to look at the structure of the variance covariance matrix. Again, over here you have a variance as the diagonal items or elements in the matrix, and off diagonal items corresponds to the covariances between those. Again, previously, none of these covariances are considered, or at least the covariances of field modeling and thermohydraulics between and the cross sections or nuclear data are not considered. So, as a case study, we're looking into 3 Mile Island Unit 1 benchmark case. This is available in the UAM benchmark. Here is a cross-sectional view of the reactor core. It's a large LWR, PWR reactor. The diagram below shows a little bit more information about each assembly of this area. You have the enrichment and purple poison and the control rod location information. We use a couple trace parks model to simulate this reactor. This is a conventional tool, which is considered to be a conventional tool. It is fast running, and at the same time very accurate, widely used by the industry and regulatory body. I need to mention one thing though. In this presentation, all the calculations I'm showing is not generated by the so-called high fidelity codes. High fidelity, well, this just because of we're more focused on the production codes. We're focusing on the codes that have been widely used by the industry and regulatory body, and it also because those codes are fast running and is more suitable for the sampling-based approach when performing a certain quantification. If the focus is shifted to the high fidelity codes. In principle, though, all those methods are still applicable, but you won't get the results as quickly as using the production codes like this. There are three cases we looked at. First one is a full power steady state simulation. Second one is the control rod ejection transient. Third one is a cycle depletion calculation. The table shows the input parameters considered in this study. The yellow one is the one that has only has impact on one physics, which is neutronics calculation, and the one in blue has impact on two physics, which is neutronics and field performance. The three in green have impact across the board on all three physics. The ones in white are currently not considered in the study, but will be considered in the future study. So just to explain more why certain parameters have impact on multiple physics, let's take manufacturing tolerance, for example. T gap means gap thickness, T clad means cladding thickness, and R fuel means the radius of the fuel pallet. It's understandable that all of them has impact on the homogeneous fuel group cross sections that were coming out from the lattice calculation, because basically you change the material composition. For thermohydraulics calculation, they have impact on the wetted parameter, cross-sectional area, and thermohydraulic diameter in a single pin model. All of those input of the thermohydraulics model in trace. For the fuel modeling part, the gap thickness have impact on the gap conductance, which is H gap. So basically, it's inverse proportional to it. The thicker the gap is, the lower the gap conductance becomes. Another parameter we look into is the gadolinium enrichment. Okay, so this gadolinium is used as burn-up rubber, and this is one of the correlations that can be used to describe the relation between the fuel conductivity and the gadolinium enrichment. So you clearly see that as you perturb the gadolinium concentration or enrichment, the fuel conductivity will change, and then the heat transfer mechanism or the heat transfer effects will be different. And it will affect, of course, the power, not so much the power, but the temperature. So if we follow the approach I described earlier, and we perturb all those parameters consistently, and we eventually can construct such a global variance covariance matrix. This figure is here just to show how it looks like. The majority of this matrix is occupied by the cross sections, so this part. At the lower right corner, you have a few parameters such as the gap conductance and the fuel conductivity and others I mentioned in the previous slides. Those are the input of the fuel performance model and thermohydraulic model in that trace parks coupled system. And here I'm giving you a sense of dimension of that matrix. It's a very large matrix. So once we have this, we can resample by performing Cholesky decomposition, which is typical sampling technique. And we perform 93 cold runs, and we get results for certain uh, parameters of interest. I want to mention first, before we look at the results, that for the um, if the results are given as the mean and standard deviation or the uncertainty, what really it means on the standard deviation is that this 93 code runs will have impact on the confidence interval of the number you see. Of course, you know that the more we run, the tighter the confidence interval will be. 93 is not in any means a large number. We pick this number because at the same time we want to analyze some tolerance limit, such as peak field temperature, peak reactivity, and we want to look at the 95 percentile with 95% confidence of those parameters. And this is suggested by Wilks' formula. So when I show the results, keep in mind if they are given in mean and the standard deviation, we do need to apply this confidence interval to the standard deviation. So the first set of results are given in this table. It includes the eigenvalue, the axial power distribution, and the radial power distribution. You have uncorrelated case, which is before the correlations are considered. And then the correlated case, this is when the covariances are considered. So if you look at this number, I know it's very busy, but I just want to quickly point out that you do see a little bit reduction in the uncertainty when you compare the uncorrelated results with the correlated, or when you compare the correlated results against the uncorrelated results. So if you use this as a reference, you do see that there's a slight decrease in the uncertainty of those values. It doesn't change really much of the mean value. All of them are very, very close. But you do see a slight difference in the uncertainty. So that's the first impression. If you included the covariances in the calculation, you may end up with lower uncertainty. We also look at power distribution. Each of this plot describes power, assembly power, relative assembly power in a quarter core representation. So the first number in the box is the relative assembly power. Second number, or number below it, is the one standard deviation. Same thing happens if you compare the correlated case against the uncorrelated case. You do see a slight decrease in the uncertainty, although you don't really see much of change in the mean value. If you look at all those boxes, each representing one field assembly, you don't see much change in the mean value. So this is at the beginning of cycle. Same happens at the end of the cycle. Almost the same of the mean value, a little bit decreased in the standard deviation. Okay, and then we look at the depletion part, where we deplete this reactor for an entire fuel cycle, 664 days. And then we look at the end of cycle burnup of each assembly. The number over here is gigawatt day per metric ton of uranium. And you see that, again, not too much of difference in terms of the mean value, but really there's a decrease in the relative uncertainty even in the one standard deviation. So then we perform a transient analysis on the control rod ejection, where one control rod is ejected in a very small amount of time, which introduces large positive reactivity. And as a result, you may expect reactivity to increase and the power and temperature to increase. We perform both correlated and uncorrelated calculation at the beginning of cycle and end of cycle. Here in the table, you have the peak core reactivity, peak core power, and peak field temperature. I'd like to mention that the results here are not mean plus standard deviation, but it's a mean plus the 95th percentile of the results minus the mean. So basically, you are looking at the if you add those two numbers together, you're looking at the 95th percentile of core power fuel temperature and reactivity. Okay, and you know we can just look at those figures to show the impact of this covariances. The blue one is the original calculation where no covariances are considered. And the red one is when you consider those correlations. And you can see, again, always you see there's reduction in, in the 95th percentile of the peak value of the fuel temperature. This is the beginning of cycle, this is end of cycle. So beginning of cycle, we achieved 97 degree Kelvin of reduction. And then at the end of the cycle, this reduction is about 11 Kelvin. What that means is really by considering the correlations of the input uncertainties, you increase the safety margin in various degree, somewhere between 37 to 11 Kelvin. And that really means you have gained some operational space for the reactor. So this is a summary of the first part. I will not repeat this, but really there are some challenges. For example, the global VCM, the matrix, is very large in dimension. This will further increase when you include more, input parameters. And so we really have to find a way to reduce the dimension and this resampling more efficient. And of course, we want to look at the sampling size approach to determine a more reasonable size. And we will then extend this study to more transient analysis. So that's the first part. Here are some references. The second study is on a fast reactor application. The work is primarily done by Andy Rivas, who is a graduate student in our group. And this is in collaboration with Argonne National Lab. Nicholas Stoff and Tyler Sumner are the collaborators in this project. And we have a publication accepted by Nuclear Engineering and Design. I certainly will let you know when this paper come out. So this study is really about the fast flux test facility. For those who don't know this facility, it's a 400 megawatt sodium cooled fast reactor fueled with MOX fuel and has been operated for 10 good years. It's a prototype liquid metal fast breeder reactor. It's a national research test facility. Now, over the years, a lot of pressures measurement data has been collected, and the International Atomic Energy Agency has created this Coordinated Research Project (CRP) to provide to support the validation of the sodium cooled fast reactor analysis tools and methods, and also provide the community with valuable benchmark opportunity. So that's why Argonne and NC State participated in this study, and the transient or the scenario we're looking at is the so-called loss of flow without Scram test that was performed in 1986. So what it is that you turn off the coolant pump a certain time during the normal operation, and then you want to test if you have enough safety margins for this liquid metal cooled reactor, and also collect the data for the computer code validation, and also to demonstrate the passive safety features. One of the safety features is the so-called gas expansion module, the GEM. Right. So the way it works is very simple. If you have pumps on, you always have the sodium filling this tube, and that will prevent some of the neutrons leaking from the system. But when the pumps stop, while you're losing coolant to the reactor, you also lose this shield to the neutrons. And as a result, the neutrons will leak out of the system. And keep in mind that the leakage effect has a strong impact on the reactivity to the fast reactor, much stronger than to the thermal system, such as light water reactors. So one of the reasons they did this transient is to show, okay, with this passive safety feature, we can actually transition the reactor to the decay heat power level without really having to scram the system. And it was successful. So how do we model this thing? Um, there are two parts. There's the neutronics analysis, there's thermohydraulics. Neutronics really focus on the core calculation. So this is the core model. We use ARC system, which is um, developed and maintained by Argonne National Lab. And we generate cross section using MC square, use diff3D to calculate neutron flux distribution and percent to perform perturbation theory analysis and to get this reactivity feedback coefficients. If you remember, in the fast reactor I just mentioned, in the fast reactor, we're going to use all those feedback coefficients to in the core and system calculation to calculate the feedback on the reactivity and using a point kinetics model. So these are the ones connects the first step and second step of the whole core system coupled calculation. And the table shows how those different feedback coefficients are calculated and what type are they. If they're global, it means the single value of this parameter will apply to the whole core. If they're local, it means at a certain location, radial or axial, you will have to vary this number based on material, based on the location of that computational node in the reactor. And there are two so-called PIOTA, proximity instrumented open test assembly in the reactor, where thermocouples are placed to measure the coolant temperature when they exit the reactor. This is the second part of the calculation using the SAS code to perform the thermohydraulics calculation. I will skip the details of this model. This is radial configuration, and this is axial, the pin model in thermohydraulics. So in the best estimate calculation, we compare the results against the measured quantities, such as net reactivity fission power and the two coolant temperatures, exit temperature at PIOTA 2 and PIOTA 6. Okay, you can see that we have very good agreement on the net reactivity. The blue ones are the calculation results, and the orange curve is the measured data. So for the reactivity and fission power, very good agreement. But then there's a certain deviation in the PIOTA 2 temperature measurement and a relatively large discrepancy in the PIOTA 6 temperature measurement. So the question we're trying to answer here is, can the correlated uncertainties coming from nuclear data explain at least part of the observed discrepancies? And we're turning to nuclear data uncertainty because they affect the estimate of neutronic reactivity feedback coefficients, which in turn affect the predicted reactor response. So coming back to the calculation flow, two-step. The first step is to really generate the feedback coefficients from the data. And the second step is to obtain the system responses using the feedback coefficients. So if you want to properly propagate the uncertainty from nuclear data, you have to first propagate the uncertainty to the feedback coefficients, right? So we use something called sandwich rule to do this. And as a result, you get feedback coefficients at the uncertainty of the feedback coefficient, but also you get the covariances of those feedback of the feedback coefficients. And then you can sample the covariance matrix of those feedback coefficients prior to the system calculation. And then you can collect the results and perform statistical analysis and to get the response. There are two types of correlations needs to be considered. One is called spatial correlations. These are really the correlations between uncertainties in different core regions. For example, the center of the core and the outer core. And the second part is the coefficient-wise correlation, which really is the uncertainties between different reactivity feedback coefficients, such as Doppler and the GEM feedback coefficient, for example. So the first we look at really how much uncertainty of each feedback coefficient have in terms of the contribution from different isotope and the reactions. The cells in the three feedback coefficients in yellow means they're global. The rest are local feedback coefficients. And the quick takeaway from here is that sodium scattering cross sections, iron 56 scattering cross section, contribute largely to the GEM uncertainty. GEM again is the passive safety mechanism we're talking about. So it contributes about, as the total uncertainty of this feedback coefficient is about 5%, which, although the number itself is not the largest, in this row, but in fact, as you will see later, because the system is extremely sensitive to this feedback mechanism, so that 5% really matters a lot. Then we consider two cases when we propagate uncertainty. So the first one, case one, is the fully independent, which means we only consider the diagonal terms in this representative or simplified case of the matrix. The C's here, C1 and C2, are the feedback coefficients. So you have two, just to show the idea. And you have two spatial regions as well. So each of them have two spatial regions. And if you consider just the uncertainty itself, which means you consider just the diagonal terms. The second part is when you extend it, you include the second part, the number two, or the orange ones. These are the ones corresponding to the spatial correlations. And then case three is the ones plus the threes. The threes are the coefficient-wise correlations. And then the last case is fully dependent, where everything in this matrix is considered. That's the most complete case. And then we'll perform a resampling scheme following the Cholesky decomposition, which is, again, nothing fancy. I will just skip this slide. So here's the results for the uncertainty quantification of the fully dependent case, or case 4 that we mentioned before. Over here, we're comparing the measured or the calculated net reactivity, which is in blue, against the measured net reactivity during the transient. Okay, so you can see that, and then the measurement data is plotted in black. So the first thing to notice is that there's a fairly good agreement between those two, up to 1,000 second. Well, it's 1,000 because we started simulation at 700. That's because that we run the simulation for 700 seconds to reach to a steady state, to reach the converged solution. But then basically what that means for the 300 seconds or so, the agreement between the calculation, calculated results and the measurement data are great if you consider all the nuclear data uncertainty. Okay, and then all the rest, the curves in different colors represent the different components of this net reactivity. For example, let's take the two largest one. The one over here, the purple one, is the one from GEM, the gas expansion module. So what it means is once you stop the pump, um, the sodium in that tube that's shown in the previous plot would disappear, right? Because there's not enough force to push it, upward. And as it disappear, you create this hollow region where neutrons can just leak, just travel out of the system. And because of the strong impact of the leakage on the reactivity, really it creates a lot of negative reactivity, as you can see here, about $1.5 negative reactivity. Okay, and at the same time, you get this positive feedback from Doppler. That means your temperature is decreasing, and that is a result of negative reactivity insertion from the GEM. As the temperature of the fuel decreases, you insert positive feedback just because of Doppler itself. And so these two are the drivers of this transient. And of course, you have other um, feedback mechanism, right? One noticeable one is the radial expansion, which is a red one, which also contribute negative reactivity. But really, what it shows here is that the gem, dominates the whole transient scenario, or the feedback mechanism. Here is a comparison of fission power, the temperature measured in Piota 2 and Piota 6. One thing to notice is that when we consider the nuclear data uncertainty consistently, right, of the correlated uncertainties, we're actually able to cover most part of the measured temperature in PO2 up to 1,000. Afterwards, it deviates and you see noticeable difference. And that is because the system has transitioned completely to natural circulation. And that probably is an indication of something is not correct in the model to fully capture the natural circulation effects. But you do see there's still a relatively large deviation in the temperature calculation prediction in Piota 6. Remember that Piota 6 is at the core boundary, so which means that you should not only consider the uncertainties or correlated uncertainties in the fuel assemblies, but also need to consider those associated with the reflector. But this is something that we missed in the calculation. So we suspect that contributes much of these differences. Of course, further study is required to confirm this, but that's our suspicion at the moment. So one other thing we did is to really perform a sensitivity analysis to show how much a contribution there is from different feedback coefficients, right? And the first column of here shows the total uncertainty if all those parameters are perturbed at the same time. And then all the rest shows the impact or the percentage contribution from each feedback parameter if they're independently or individually perturbed. And I take the net reactivity, for example, the total uncertainty is about $0.125, but 99%, over 99% of that is contributed by the gem. Okay, so that clearly shows the gem dominates the whole feedback mechanism, right? That's actually the same for almost, or actually for all the parameters. And so you do see the importance of this inherent, feedback method or the safety mechanism they implemented in the system. And then last thing I want to mention is how important it is to include the correlations in the uncertainty. Remember that we have four cases related to this matrix. The complete one is that everything in this matrix is considered, and then that's what we call dependent, fully dependent case. Okay, here you have the uncertainty when all of them are considered consistently. And then this is the true value or the absolute value of the uncertainty. Then you remove one at a time um, until you have the fully independent case. Only the cells marked in one are considered. So that relative difference in percent is the difference between the dependent, fully dependent, and the independent case. You can see there is certain level of difference up to 10% that are different. Then as you add twos and threes in the matrix and then consider in the propagation, you start add up to the fully dependent. So this approach actually shows the importance of those correlations. Even though I would argue up to 10% of difference are um, you know responsible for the difference. It's still very important to consider those covariances in the uncertainty. So with that, I think I conclude the second part as well. Here's a quick summary and the references. One thing I want to mention is really um, um, over here, you see that if you remove the correlations from the fully dependent to the independent case, you actually have a reduced uncertainty. But if you recall, in the light water reactor case I just showed earlier, the effect is the opposite. If you include those correlations or covariances, you end up with lower uncertainty. So this is something that we want to look into further because we just got the results recently. We want to compare the light water reactor system and the fast system to understand why the effect in those two different systems are the opposite. So with that, I conclude my seminar. I welcome any questions you have.
All right, thank you very much for an awesome talk. If the participants would prefer, they can either post questions in the chat or you can raise your hand and unmute your microphone and ask questions that way. So any questions from the audience? It's the first talk of the semester, man. Everyone's shy. Okay. Oh, hang on. We got one from someone you might know. Professor Turinsky is asking, as part of the verification, did you have problems showing that the covariance matrices are positive definite?
I can say for sure in the light water reactor case, we do not have a problem. Although I remember we have a discussion on this, but eventually we noticed there's no issue with a positive definite. In the fast reactor case, we haven't, well, at least as far as I know, we haven't really looked into that. But if you have that issue, my understanding is that you can't really perform Cholesky decomposition, or you have issues over there. So my answer for now is no, but I can definitely follow up if I'll dig into this and I'll come back to if the answer is the opposite.
Thank you very much for the question and for the answer. And obviously, you two know how to get in touch with each other if there's any follow-up. Any other questions from the audience? Okay, we're getting up on 5 o'clock, so I will start with the traditional going once, going twice. Usually this is when everyone starts raising their hand, but I believe, Jason, you are off the hook. And I want to thank you for a really good talk. I want to thank everyone for being a great audience and looking forward to seeing everyone next week for Harsh Desai's seminar talk. So thank you very much. Welcome back. And look forward to seeing you all on Zoom or hopefully face-to-face in the near future.